So yeah, I'm not going to. Uh, so okay, so this is what we're gonna do. Okay, okay, can you prove this? Everybody know the proof for this, right? This is the last lecture in probability, no, in optimization. Presumably you're doing convex optimization. Can you all prove this? All right, of course you can, but we'll remind you what the proof is. Okay, so a hyperplane is sort of, this is what it means. There's a V where V dot X is less than V dot B for all X and P. So again, let's parse this. B is a point. Okay. B is a point, and here's your convex set. Okay. And so now for every X, this is the X here, and every B, for this B, V dot B is on one side of the hyperplane. It's positive, right? That's what V dot B means, being positive, right? So it's greater than, or it's this side of the hyperplane. And V dot X is this side. Okay, does that make sense? Is that clear? The hyperplanes? Yeah.
Just to clarify, this is like the separating hyperplane theorem, right?
Yeah.
Okay.
Yeah. So for every convex set, this is true. Do you see a proof? Like now you see what the statement is? Okay. So what's there's this one is kind of telling you. In fact, it's giving you a hint of the proof. There's a point P sort of in the convex body where the separating hyperplane is in fact B minus P. That is a vector, right? You can use B minus P as the vector. Is that reasonable? Is that clear? And what point is this? Which point is it in the convex body where this will happen? Do you see anybody? Which of the points in the convex body, or maybe it's more than one, but which is one point in the convex body where the hyperplane defined by B minus P is a separating hyperplane? Anybody? Okay. Well, I'll tell Garija to put some things on the exam. So I'm kidding. I wouldn't know this either. Yeah, but I know it because I read the slides already. But yeah.
Sorry, just making sure I understood.
Yeah, part of it is parsing. I agree. Okay, so what is it? Yeah, go ahead, parse it.
Making sure I understood the question. Were you asking which point in the convex set?
Yeah.
Satisfies them?
Yeah.
Isn't it supposed to be for every?
No, what I'm saying is I'm going to build the hyperplane. And the second line is the proof here. You see the second line here? Okay. So what I'm saying is that, I'm saying that a separating hyperplane, this is a vector, right? B minus P is a vector pointing from P to B. I'm saying that's the hyperplane.
Oh.
That's the normal to the hyperplane. When I say hyperplane, I'm often talking about the normal to the hyperplane.
Oh.
Right? Does that make sense? A hyperplane is defined by its normal. Sorry. A hyperplane is defined by its normal. So when you're on one side of the hyperplane or the other, that means you have different values for the dot product with the normal. Remember that from high school, the cosine theorem? Dot product is a cosine or something. It's the length of your projection along the hyperplane in that direction. Okay? Does that make sense? Okay. Like, I don't know, for those of you who were in 70, I claimed everything in 70 was in elementary school and middle school. Here I'm claiming it's in high school. So, okay. So, and really, convex optimization, a lot of it is two-dimensional. Right? This is just a two-dimensional picture, and it actually does capture what's happening. Okay? Essentially, we don't seem to reason much better than two dimensions, so that's what we're doing. Is that okay? Okay, so this is this vector. B minus P is this vector. What point in the convex set should you use for this vector so that this vector, the normal, defines the hyperplane that separates it? Yeah. This boundary point? Yeah. The closest one. Okay, great. So now you can take v to b minus p. And then that satisfies this thing, right? Because along this vector, in this direction, there's some value along this direction where all the points over here, the dot product with this vector is greater than something, and all the points over here, the dot product with this vector is less than it, right? Remember cosine, dot product gives you the projection in that direction. Okay? Okay, so for a convex point and a point, B and A, there is a point where if B is, either B is in A, either the vector B, the point, I didn't illustrate the case before, but B could be in A in this convex set. There's no separating hyperplane, obviously, right? Okay, so here, or there's a point where this holds, okay? And that's what we're going to do. We're going to choose P to be the closest point, okay? Now, how do I argue this is going to work? Okay, so now what's going to happen is the following. Now I'm done. Okay, that's not quite a proof, but, or, right, either it separates it, or what happens is there exists an x in P where x minus P transpose times B minus P is greater than 0. Okay? Now, why is that? Now, if you think about it, right, if either this satisfies it, right, either it's done, like the condition we wanted is this is less than 0 for all x and P, less than or equal to 0. Okay? Does that make sense? And now what has to happen is if we're not done, this is the negation of that statement. Let's look at the picture. So what this means is there's this vector in this direction, okay, and this dot product is positive from x to p minus x. Okay, it should be x minus p. Yeah, x minus p. This dot product is positive, right? Because that's what this says. The dot product's positive. So that means this angle is what? Is it bigger than 90 degrees or less than 90 degrees? Less than 90 degrees. So you're kind of going in the direction you want to. Okay? So that means, right? Is that clear? So there must be a closer point to B. You're going, I mean, up here, x may not be closer to B, right? Because x is way over here. It may be farther from B than P. Okay? But somewhere along this path, right, this B, what I'm doing here is I'm drawing a circle. Okay? The tangent would be at a right angle. The circle is all the points at the same distance from P as from B as P. Right? That's the circle. And this since this is less than 90 degrees, and the 90 degrees is what the tangent would be, you must be going inside the circle. Okay, so that's a geometric proof. Does that make sense? Okay, this is a proof of the separating hyperplane there, which is absolutely fundamental in optimization. Yeah.
For the first part, we're done. But what is the case if it does?
Well, if this is not true, if there does not exist an x in the polynomial, we already have a separating hyperplane. B minus p is already a separating hyperplane. Okay, I should have said, yeah, right. This is the condition. We're done if this happens. For every point, x. Right?
For every point x in P?
Yeah, in the convex body.
In A?
Yeah.
Okay.
This should have said it for every x. Yeah.
So in the case where we're not done, we didn't actually pick the closest point?
Yeah. That's the contradiction. Right? I start with choosing the closest point and saying that should work. Either it works or it doesn't. If it doesn't work, then I can show you there's a closest point, which is a contradiction. Yeah.
Intuitively and visually, the 90-degree angle argument works, but
Yeah, we're going to do more.
Okay.
Yeah, so this is a contradiction. Contradicts the choice of P as being the closest point. Is that clear? Really, that's a high school geometry, right, once you set it up. Is that clear? And I'm going to do more high school geometry. Okay? Okay, so this, I'm taking this picture over here to the left that we saw on the last page, right? This is the circle around P. This is the point X, this is point P. We presumed that P was the closest point. And now I'm going to argue that there's a closest point, and I'm going to do it quantitatively using trigonometry, okay? So what we say is the following, right? What we say is, okay, there's P minus B. This is this vector here, right? This is this vector here. And now we have this angle, right, which is theta. Okay, we know theta is less than 90 degrees, right, because there's a projection in this direction. So, and then there's point X. So this, I'm moving along this line here. I'm moving along this line here. That's what I'm thinking of, okay? So L is moving along this line. Does that make sense? What we're doing is we're moving this distance along this line. Mu could be 0 or it could be 1. If it's 1, you're at X. If it's 0, you're at P. Does that make sense? So the mu is moving along this line. Okay? Yeah.
So is the intuition here that we're moving along the line to try to see if B is actually the closest point?
What I'm going to do is just solve for a mu that's closer.
Okay. So
Right.
that's the purpose of moving along.
Yeah.
Okay, thanks.
Yeah, I'm going to find a point here that's closer than P.
Okay.
Or, I mean, but in fact, any point before here is going to be closer than P. Okay? But this will be the closest point. I'm going to find the closest point, okay, along this line. Is that clear? So I'm going to use calculus a little bit. All right. Okay, so now what's the square distance to B from this point, this moving point, right? Once I have a mu, I have a point, okay? And when I have this point, I'm using Pythagoras, right? There's this plus this squared plus this squared square root. Is that clear? Okay. Okay, so that's all I do. So let's just calculate this. Do you see why this is that? Well, along this point, the projection on the line is L cosine theta, right? This is, again, from high school, right? L is the length of this line. Okay, it's L cosine theta. The projection along this line is the rest of it, the length of P minus B, minus this projection. So that's what this length is. Okay? And now this length is sine, right? This length is L. This is the hypotenuse. Is L sine theta. Okay? So that's the whole figure. And now I'm trying to compute the length of this line. And I do the squared, right? I take this squared plus this squared. Right? Okay, now that's just some square. It's a little nasty. Where theta is this angle, right? And you can simplify. Okay, so this is just doing the square out, I think. Where'd the sine squared and the cosine squared go? Yeah, sine squared plus cosine squared is 1, right? So maybe it's late middle school. Okay, now you have to take a derivative, which is maybe high school. Okay, so there's mu here, right? And so you take the derivative to try to minimize this. You're trying to minimize the line. Okay, so you can do some fancy stuff. All right? Okay. So, yeah, so this is a, absolutely critical concept in, I hope, in convex optimization, right? So it's like a pretty simple proof. Okay? This is why convex optimization works at all. Okay? So, I mean, in some way. Yeah, and so moreover, what you can say is you can take the derivative and you can say this is negative. If the derivative is and this derivative is negative because this is negative, right? Because cosine theta is what? It's positive here. Okay, so this is negative, and this is positive, but that tells you as you go further away, you're going to get larger, right? If you go forever along this line, it's going to get bigger. That's this term. Okay? Okay, great. Okay, so this is sort of a, you've seen these. You've seen this theorem of alternatives, right? You either have a solution to these things or you have a proof you don't have a solution. Okay? Maybe you want to find a point B in the polytope, and that's you want to find a feasibility thing, or or it's not in the polytope, right? And then you can prove it, right? You've seen duality. Have you all seen duality? Okay. That's what it is, an alternative. What's another alternative you saw again in high school? When do linear equations not have a solution? Parallel lines, okay? Or another way to say that is when you can add them up and get 0. Right? So that's just another problem. How do I add up these equations to get 0? So that's the dual problem. Okay, there's a primal is to try to find a solution to linear equations. To prove that there might not be one is you want to add up the linear equations to get 0. Okay? Right? So here you have, you use row reduction to get 0, the 0 equation times x. And then the right-hand side, b, is not 0. Okay? If there's a way to add up the rows and columns, rows of A, so that on the left-hand side you get all zeros in the matrix, and on the right-hand side you get a non-zero, you know there's no solution. And that is, again, just solving another linear equation. It's the dual. Okay? There's this theorem of alternatives. Okay, so that means this is what it is. This is a linear equation, right? You want to find y, where yt of A equals 0, and yt of B is not 0. Yt of the adding up the entries of the right-hand side is not 0 in the same way. Okay, so it's sort of a thing, right? The space is the image of A. The affine, the subspace is a subcolumn, a column span of A, and y is normal, right? What is y now? Y is normal to every column. Does that make sense? The dot product of yt is a normal to every column. So it's normal to your whole space. So you found a separating hyperplane. Okay? You found the normal to your hyperplane. And you've proven that the right-hand side is not in your affine subspace. Okay? So this is like, the separating concept is central to everything, because it tells you whether you have a proof or not a proof. Okay? Okay. And you can generalize this if you have two convex bodies. And they're different. They're separate. There's a separating hyperplane. And again, the idea is the closest pair of points in the two planes. Okay, but I'm an algorithms person, right? I like algorithms, right? I guess maybe you don't know that from 70, but I used to often teach 170. I really like to see everything as an algorithm. Okay, but this is an algorithm, right? You find it, you say, well, there's a point that fails, I can go toward it. That's an algorithm. Okay? So that is an algorithm. That proof is an algorithm. You can get closer and closer. Like I use contradiction and stop, saying, in math, they say, assume I have the closest thing and I have a contradiction. But that's actually, in this case, it's an algorithm. I assume I have a closest one, but I produce a closer one. So in fact, I could start with any point and produce a closer one. And once I produce closer and closer points, with this method, I'm running an algorithm. Does that make sense? Okay, so convex optimization is also about algorithms, right? And so this proof embodies a particular algorithm. Now the convergence of it, right? You can see this here, right? AX equals B, right? That's another one of these convex optimization problems, right? It's a linear system. It's a fairly simple one, and it's simple to sort of think about. So A times X is the closest point to B in the affine subspace. Now, an affine subspace is just a plane, right? Which is not quite a convex body, but it's essentially the same thing, right? Any 2 points, there's a point in between. Okay? So if you start at a point, how do you get closer to B? If you start at X, how do you get closer to B? What's the point in the direction of B? Yeah.
Wait, sorry, how is hyperplane not a convex body?
It goes forever.
Wait, so convex has to be finite?
Yeah. It's an affine subspace, meaning it goes forever. A convex body means there's 2 points. For every point, there's 2 other points where it's in between. It's somehow not, because it goes forever.
Okay, so like R2 wouldn't be.
Yeah, it says that an affine subspace says for any x, alpha times x is also an A.
Wait, then why is a line a convex?
It's not. It's an affine subspace. I mean, okay, just call it convex. Well, if everybody's happy with that, we could call it convex. Everything that works for convex works for affine subspaces. It's just technically a difference. I can't think of it right now, but I'll try to do that later. Is that fair? Okay. Just think of an affine subspace as a convex body, but it is. It's somehow it's weird because you keep having to find things in between two others, and how do you deal with the points at infinity? So I don't know how to do that, and I think you can't. Yeah.
Wait, so this problem of finding closest, that's least squares, right?
It's least squares.
Okay.
All right.
So it's not actually equality.
Well, least squares if ax equals b gives you b.
Okay.
It gives you a solution because the value is 0.
Okay.
Yeah. Okay. Yeah. Okay. So what do you move in? So you do the obvious thing. What is this? Have you seen this? B minus ax. That's called the residual. You just move in that direction. Right? That's an algorithm. That's the algorithm we saw on the first slide. Kind of move in the direction toward the point. Okay? Okay. So it's not quite the thing because you may not be able to go in that direction, right? Because the convex space is not exactly, you may be on the boundary of the convex space, right? It may be pointing out. You can't go in this direction. If this does not have a solution, you can't necessarily go in that direction. So what are the feasible directions you can go in? The columns of A, right? That's the directions you can go in, right? Because your x here, what is each xi multiplying? It's multiplying a column of A. So it's adding that vector to your solution, okay? So you can only move in the directions of the columns of A. Is that clear? Okay. So so this is an algorithm. Already I gave you an algorithm, which is just like, okay, move closer to where you want to go. That's it. And, okay, well, you can't get out of this subspace, so you have to, the subspace happens to be the columns of A. What do the columns of A do for this one? They give you exactly, right, they may not be like this. There's something they tell you how to move inside of your subspace. Okay? This minimizes the least squares. Okay, so what will happen is eventually, if this point is outside of the subspace B, it will go until it can't move any closer, and B minus AX will be orthogonal to all the columns of A, right? And you can't move closer. That's the closest point. Okay, so this closest point algorithm is actually central to all the algorithms you've seen. Not central to all the algorithms. There's fancier stuff that happens. Okay, so now you get convergence, and now you've probably lived in this sort of nasty nightmare of trying to understand when things converge and stuff, and that all depends on the size of the columns of A and the size of the numbers and the angles you're moving in, right? If this angle is little, that depends on the size of A and the numbers, right? So then you have to do a lot of work. But in spirit, this is a lot of what you're doing. Okay? So okay. So now I'm going to talk about sort of naive other algorithms, really very simple algorithms, and actually talk about convergence a little bit, on how to do convergence in sort of simple cases. Okay? Okay, so here I'm going to move a little bit toward learning, but really this is how machine learning and optimization are the same, right? Or at least very closely related. So I have a separable set of points and a perceptron, and I'm going to prove a performance bound. So the problem is the following. I've labeled points with x1 through xn. Have you done the perceptron? You didn't do the perceptron. Okay. I know you didn't. Okay? So now you have a hyperplane separator. Okay, you can learn this concept. Or you can separate the plus examples from the minus examples with the hyperplane. Okay. And moreover, you have margins. Like, it's pretty good. Like, everything is at least, this is where convergence matters. You have to, like, look at the parameters of your problem. Okay? Yeah.
So I don't know if perceptron, you do SVM, so this is the same, like...
Yeah, let's not talk about SVMs. Let's just do perceptrons.
Okay, but it's the same, like, principle.
No, let's not talk about SVMs. Okay. Yeah, just a hyperplane. Okay. You talked about SVMs in this class?
Yes.
How do you talk about SVMs without perceptron? Okay, but that's fine. Okay, so, yeah, but let's just talk about perceptron, which is just finding a hyperplane separator. SVMs is a hyperplane separator too, but let's not talk about it. Okay? Because I don't think you understood it. right? Because you put some weird dual and blah, blah, blah and said something and whatever. Okay, but you need to have a picture of what's happening. Okay? So, right, this simple picture, right? From, in high school, you shouldn't have known this. And it's sophisticated. It's really what's happening. Okay, so let's just put the points, assume the points are on the unit ball. For convergence, this is what you have to do. You have to deal with all the numbers and make sure things are kind of clean and stuff. Okay. And this is called the margin. It means that every one of these things is not only on the correct side of the hyperplane, it's reasonably far from the hyperplane. It's a good, things are not right on the border. Like, then you can't really tell what that point is anyway. Okay? And it's a hyperplane. Again, a hyperplane is defined by its normal. Okay, this is its normal. And w times x is greater than lambda for all the positive points, or what is this, gamma, for all the positive points. And it's less than negative lambda for all the negative points. We're just assuming everything's at 0. He asked, is this the same as a hard margin SVM? I don't know. Yeah. So, yeah, probably, but I don't know. Okay, so I had a slide about hinge loss and all that stuff, but this is just too complicated. You can always do this on your own. Okay, so does everybody understand the problem? You're given a set of points. You want to find this hyperplane. Okay? Okay. And it's about algorithms. I don't want somebody to say, oh, you just use this blah, blah, blah algorithm as a black box. I want you to understand everything. Right? Everything. Okay? As an algorithm. Now, I mean, I'm not asking you to understand the hard margin SVM because that's not what I'm focused on. I'm focused on the algorithm. Okay? Okay, so you get this. Okay. Okay, let's just put the points on the unit ball to make it a little easier. Okay, we're going to assume all the points have that the center of the ball is at 0 and all the points have norm 1. Okay, just to make the convergence thing sort of easy to deal with without all these crazy complications. Okay, so remember again, w times x is if it's a unit vector. If w is a unit vector, it's the cosine, right? The projection. Is that clear? Okay. Now what we're going to do is we're going to assume that we only have points with a positive label. Okay, and that's good enough because if we throw these out, this still is the only hyperplane that does that. And in fact, you can actually just negate all these points, right? You can negate all these points and pretend that their coordinates are negative x minus 1. If you're doing a dot product, changing this point to the point on the polar opposite, the dot product changes to negative. Okay? So what it does is this mapping here maps all the negative points up here, and then that's good. Okay, so we're going to only assume we have positive examples. We're just trying to find a hyperplane where all the points are above it. Okay? Okay. Okay, so a hyperplane is called a perceptron. A dot product is it's just a weight vector, dot times something. That's what a perceptron is. That's a single layer neural net. Okay, that's what's in these deep nets, or one of the things in these deep nets now. Okay, and you can solve it using linear programming. You see that? You're just finding a weight vector where x dot w is greater than 0. So that's just you just put all the points in the rows. So this has an algorithm. Oh yeah, and we can call this fancy algorithm called linear programming. But the point of this is to come up with an algorithm. Okay. Okay. So here's the algorithm. Okay. First, I'm going to let my weight vector be x1. Yeah, now for each xi where wt dot xi has the wrong sign, okay, right? We want wt times xi to be positive, right? So if anyone is not positive, what I'm going to do, I'm going to call it a mistake. This is a mistake. So I have a hyperplane that doesn't work, okay, for this point. Well, I'm going to add this point to the hyperplane. Okay? Do you see intuitively why this is a good thing? Right? Because now the dot product with WT plus 1 is going to be larger with xi. It was too small. It was negative. Now if we multiply it by this new vector, it's going to be bigger. At. When we multiply xi by this new vector, we get a bigger number. Yeah. Okay. So, so there you go. So the algorithm only makes this many mistakes. After that, you have a hyperplane that separates all the points. Okay? So if the margin is larger, if it's very large, you don't make very many mistakes. Is that clear? Okay. Okay, so let's say we make a mistake. That's the only thing. We only need to analyze this when we make a mistake. When we don't make a mistake, we do nothing, right? With the hyperplane. Okay, so we're counting up the number of mistakes. Okay, so WT plus 1 dot xi is WT plus xi, right? Dot xi, right? Which is WT dot xi plus 1. Okay, so this is exactly what I was saying. This new hyperplane now has a higher dot product with xi. That's good. But we don't care only about xi, we care about everything, right? Okay. What we really want this new hyperplane to do is, this is a step in the right direction, sort of. At least it's good for xi. It may not be good for anybody else, right? But at least it's good for xi. But what we really want is for it to be good with respect to, let's say w, I should have said this. W is the optimal solution. The optimal, w is the correct hyperplane. This is w. Okay? So what you really want is you want the hyperplane you're trying to find to go toward w. Right? Does that make sense? Okay. Or to be more like w. Okay, so what we said so far is it's more like xi, because we've added in an xi. You add in a little bit of me into you, you're going to be more like me. Okay? So what I'm going to say here is I said this WT plus 1 dot xi gets bigger, but what I really would like is that WT plus 1 is more toward the right solution. Okay? And now I'm going to claim that it is by a little bit, by gamma, which is the margin. Okay? Okay. So it's a gamma in the right direction. So WT plus 1 is more like the real solution. Yeah?
Are we normalizing WT plus 1?
No. Okay. He asked a crucial question. Are we normalizing WT plus 1? It's more like, this is true, you've made WT plus 1 larger. So you can be more like everybody if you want, just by making it larger, So there's that's not, it's kind of cheating, but we'll deal with that. Okay. But at least this dot product gets bigger. Okay? So you're right. We're going to have a problem because just making a dot product bigger, I could have just scaled it and the dot product would have been bigger. That's not what we're doing. Okay? Okay. You make a mistake on a positive xi. They're all positive. Let's just write it out. So we get this, right? That's just what we're doing in this line. This is the distributive property. Okay. What is this? What is xi times w? What was our assumption? It's positive, but more than that, what was our assumption? There's a margin, right? So what is wxi times dot w? What was the margin? How big was the margin? Yeah, for every one of these, what is xi dot w? Gamma. Is that right? That's what it means to be gamma far away. It means your projection along this line is at least gamma. Okay? Okay, so that's what we're going to do. We're going to just say, oh, well, this is at least gamma. Right? Does that make sense? Okay, so now we've proven this claim. Okay? Okay. So now I'm going to prove another claim. WT plus 1 is growing, right? Every step it grows by something. Okay? But I'm going to say it doesn't grow by too much. Now, does anybody see why this is true? In general, if you take the squared norm, if you take the square of something, you take a vector, right? We're taking a vector. We take a vector, W, and then we add something to it. The square might grow a lot, right? But what if we add a vector like this? Then does the square grow so much? No, right? If this is 1 and this is A and this is a right angle, what is this new vector? What's the length of this new vector? The squared length. You remember this theorem, Pythagoras? Yeah, okay. A squared plus 1, which is what we were saying. And so now what we're saying is, okay, right? So this is let's see what's going on. What we did is we said, we have WT, right? And we have WT times XI, dot XI, means this is an obtuse angle, right? And what is our new vector? WT plus XI. What is WT? You know this head to tail vector addition? So that means you're going in this direction. So what is this angle? If this angle is obtuse, what is this angle? Acute, right? So, and this is WT plus 1, right? It's less than a right triangle. Does that make sense? Yeah.
So is this also triangle inequality?
I don't know. Yeah, the triangle inequality doesn't work for squares in the plane.
But you said it's like the hypotenuse, right? Because x.
Yeah, you're free associating. Yeah, just do you understand this proof? Do you understand? Is it proof of the claim?
Like, what if the angles are like not obtuse?
Okay, why is this angle obtuse? You tell me.
Dot product.
The dot product with WT and XI is negative. So does that mean this is obtuse?
Intuitively, yes.
Not intuitively. You don't get to say intuitively. XI dot WI is the projection in this direction. It's negative, right? So therefore, it's less than it's this direction, right? It's at WI dot XI is the projection along this line. It's in this direction, right? So it's more than a right angle.
Like, how would you think about this in higher dimensions?
This you don't. Yeah. He asked how do you think about it in higher dimensions? You don't. When you're doing a proof, you think about the proof. The proof is a two-dimensional proof.
Sorry.
Yeah. No, I'm not mad. I'm happy. That's great. But why would you think about it in higher dimensions? We're just adding two vectors. Even if it sits in higher dimensions, can't you just think about 2 dimensions? It's 2 vectors. Yeah.
Could you clarify the point you made about assuming all the points lie on the unit ball?
Yeah, it's just I just did it. Like when you do machine learning, if you do 189, that's what you'll do. You'll scale all the points to be on the unit ball for some reason.
I see, yeah, I guess just in the picture.
Yeah, it's useful because what we're saying here, we needed it here. We needed that xi was a unit vector here to say the projection was at least gamma.
Okay.
That's why we needed it.
So, in the previous picture where you drew the points, is it those points, like the plus and minus?
Yeah, these points, the points. What you would do, yeah, they're start within the unit ball. Now I'm just projecting them out to the unit ball.
I see, not on the surface.
Yeah, I am putting it on the surface. That's what I'm doing. You're right. What I did is then once I assume they're in the unit ball. Now I'm scaling them up to be on the surface. Right. This is actually what they actually do. But otherwise, if some point is really small in magnitude, then it has less importance in your algorithm. So they do this scaling. Okay. So yeah, if the dot product between two vectors is positive, then it's acute. If it's negative, it's obtuse. Right? So it just means you're pointing away from the other vector, right? Okay. Okay. So this one's less than a right angle, and then you have you can do it with math. Let me just not right. If it's less than a right angle, it's less than if this was a right angle. Okay, and you can do it with math. You can say wi plus xi squared is equal to wt squared times, this is just squaring two things, and then you do the dot product and this. This is now negative, right? Wt times dot xi is negative. That's our assumption. So you don't have to do geometry at all if you don't want. We're just using the fact that wt dot xi is negative. Okay, so you could never think about Pythagoras if you don't want, or acute or obtuse or anything. So, okay, it's just here. This is negative, so this is smaller. Okay?
You said it's negative is
Because it's a mistake.
okay.
We're only updating when there's a mistake, when wt dot xi is negative. Okay, so now, okay, great. Okay, so, this always holds, right? Even if there's no separating hyperplane or margin, the algorithm this is not just, it's just because you're only updating on a negative, you know that the W weight is not growing, okay? Okay. Okay, great. So that's it, okay? That's not it, okay? We have two potential functions, right? We say that we're doing better. We're getting more dot product on W, but we're also growing the vector. But we have a bound on how fast the vector is growing. Okay? So when do we get pretty close to W? At least in direction. Okay? So we're tilting it. Are we actually even tilting it toward W? Who knows, right? In any one step, we may not be tilting it toward W. Okay? But on average, at the end of the day, you want it to be pretty much aligned with W. Okay, so we have this one claim, which implies that, this is by induction. Wt dot y is t times gamma. Every time you get to make a mistake, you keep adding gamma to this dot product, right? This is induction. Wt plus 1 from Wt. This one is also by induction, right? We had this one. The total norm squared is at most t, the number of mistakes. Okay? Okay, let t equals m. So this says gamma times m is less than, it's just an inequality turned around, right, with t, m being replacing t. Does that make sense? So we have an upper bound on m. Okay? And this, in general, is always less than the norm of m. Okay, if you take the dot product of m onto any unit vector, W is a unit vector, it can't be any longer. It can't be any longer than the vector itself. Does that make sense? When you project onto a unit vector, you're getting the length of the projection. The length of the projection can't be longer than the length of the original vector. Yeah. Yes.
For the claim one, for the end of the implication, what if W naught, like the first?
You're adding. You're not multiplying.
Wait, but what if W naught dot WT is negative? Then you're not starting at 0 necessarily.
Well, it isn't negative because we start with x1. I don't know. Maybe if it's it can't. Okay, let's just assume it's 0.
Okay, sorry.
Okay, let's assume the original vector is 0, the 0 vector.
Okay.
Yeah.
That makes sense.
Then you can do it. Okay.
Sorry.
Yeah, that's fine. No worries. Yeah. Okay, so now this is less than square root m because of claim 2. Okay? So here you have a gamma n. Gamma m over here is less than square root m. Does that make sense? Is that clear? So now you just solve. You just say, you isolate gamma on one side and m on the other side, and you get that square root m is less than 1 over gamma, which is less than 1 over gamma squared. Okay? Okay. Okay, so that's it. This is essentially an algorithm for linear programming. Like you don't have to do, I mean, it's a stupid algorithm. It'll be really slow in practice because we're assuming all kinds of nice things about it. But it's, it's pretty good, right? You know it completely, right? Okay. Okay, so now I was going to do a fat separator, but let me skip this. It's just sort of more stuff. Okay, what I was saying is, what's bad about this? Let me just at least say what you can do. I won't go through the proof. Say there's a separating hyperplane, a gamma, then we might find a barely separating hyperplane in this case. We used to have a really nice, beautiful hyperplane that, the good points were really, really positive and the bad points were really negative. That's a nice solution, right? No point is close to it. You don't even have to wonder about the points close to it. They're really far apart. But what it may have produced is something that's not very far apart. So maybe if there's a big fat separating hyperplane, maybe you can find one that's pretty fat. Okay, gamma over 2. Okay? So how would you generate this mistake? How would you do this algorithm? Well, in this case, if the algorithm doesn't tell you for sure it's on one side, if it's less than gamma over 2, you call that a mistake. And then you add in xi. So you could sort of say, not only do I want this algorithm to be bigger than 0 on the good points, it has to be bigger than something. Okay, so I get a good margin. Okay? So you modify the algorithm, and you modify the proof, and it can work. You have to do something more complicated because this is slightly obtuse, and you have to then bound this. Claim 1 works exactly as before. Claim 2 is a little bit more complicated. Yeah.
Is there a straight rule of find the largest / gamma that you can do this?
Yeah, that's probably what you did with your fat SVM optimization. Right. If you wrote it as a convex program and you called some magic thing that says convex programs can be solved. Right. You can. Yeah, you can. That's what it is. Yeah, that's exactly what you did with your hard margin, blah, 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 something. Okay, so he asks us a way to optimize this to make it the largest. First of all, you can just take this algorithm to a limit and not do delta gamma over 2. You could do gamma minus epsilon. And that would also work. And you would approach the best hyperplane. So, but that's fine. We can worry about that later. Okay, so now I want to talk about, this is one algorithm, right? Like whenever there's some point that was bad, I sort of just added it into the hyperplane. The hyperplane itself was the sum of the points, was the sum of multipliers times the points. And that's why you can do an SVM. Okay? An SVM works because with the kernel trick. Did you do the kernel trick? You did the kernel trick. The reason it works with the kernel trick is that actually the solution itself is the sum of the original points. And the dot products can work with this kernel idea in this larger space. Okay? So this also gives you the kernel trick in another way. Maybe you had to do something nasty with the dual to say you can do the support points with this. But this is an algorithm that gives you the same properties. Okay? But it multiplies each of the things by these in this sort of very generic way. It just adds in. It might add in 10 copies of 0.1, 3 copies of 0.2, and so on. Right? So there's other ways to do this. Is you could have used exponential. You can say, well, if this is way on the wrong side, I can penalize it more than the things that are slightly on the wrong side. Okay? So there's other algorithms like to do this, and you can play with those. One of those algorithms is this exponential penalties. If something's, you can penalize something according to an exponential to how far away it is on the wrong side. So you can do various tricks. Okay, and I could redo that whole analysis where I use this exponential function. It's called multiplicative weights. But multiplicative weights has a really broad application. So let me show you this really amazing broad application. Okay? Okay, 1 bit, 2 bits, $1. Do you know what that means? Who knows what that means? Who knows what 1 bit, 2 bits is $1 is? It means I'm really old because I know what that means. Okay, I mean, 1 bit is a quarter, and 2 bits is 2 quarters, and $1 is, it's $1. Okay, so that's it. But I never said it. Old people said it when I was young, but at least I knew what it was. Okay, so one deep net, 2 deep nets, a lot of them. Okay, so the idea is that if you have a deep net that's pretty good but doesn't solve your problem, and now you sort of feed those, then you have another, but I don't know, this kind of sucks. Let me build another one. Okay? And let me build another one. Let me build another one. And I have a guarantee that each time I build one of these deep nets, no matter what I put it in, it does pretty well. Okay? At least it doesn't terribly suck. It's a little bit better than random. Okay? That's all I want. It is crappy deep nets, just a little better than random. Okay? Can you then combine them to get something that's a lot better than random? Wouldn't that be great? If I could find a way that I have an algorithm that, for anything, it works a little bit better than random, then can I combine all these algorithms to always do well, almost always do well? Okay. The idea is you sort of do one net, and now you say, okay, these are the points that I didn't do very well on. Let me try again on those points, and then let me try again. Let me try again on the remaining. Now I'm not doing them separately. I'm not doing the same. Not doing deep nets on the same points in different ways. I'm taking the points. I'm looking at the output of one deep net, and then running another deep net to try to at least do well on some of them. Okay, that's the idea. Okay, so it's a little different than running many algorithms and combining them. It's running an algorithm, looking at what it did, running another algorithm, and every time I don't do really well, but I do a little bit better than average, guessing. Okay? And then I vote. So you're barely learning on all, and I'm going to learn really well. So, look, this is a mess, right? There's no hyperplane that separates these, right? But doing half of them is easy. I just take any hyperplane and scan until half are on both sides. So that's random. That's what I'm saying. You could randomly classify plus and minus ones using any concept easily, and do nothing. This tells you nothing, but you can do it. Okay. So a bit more. If you got even a bit more than half, 1/2 plus epsilon. Now, is that useful? That's a question. Okay? Yeah, in this case, this is a bit more than half, but okay. Okay, so now I'm saying I have an algorithm that for any set of points, it will correctly classify them a little bit better than average. Random. Okay? Better than half. Okay, now I want to get, this should be 1 minus. Okay, there's a bug. Okay, you can't do more than one fraction. Okay, so that's fine. It's a joke, right? Did you see it? This is a probability joke. Can you have a probability bigger than 1? I'm from Texas. I haven't even seen a probability bigger than 1. All right. Okay, this is what I want. Okay? Does this make sense? I am from Texas, and I haven't seen a probability bigger than 1. Okay. Do you think we can do this? Who thinks we can do it? Okay, raise your hand. Everybody needs to raise their hand. Why would I be talking if we couldn't do it? Okay. How? Okay, somebody who raised their hand, tell me how. Okay, this is the idea. Okay. Yeah, so this idea, I could have used it to do perceptron, for example. Just multiply. Instead of adding in vectors, I could have added in bits of vectors or increased their weight by epsilon. I could start with an average of all the points, and then now just weight the points differently. Okay? And then the way I would weight the points is as I run my algorithm, I would change them by an exponential, multiply by an exponential. So it's just everywhere, okay? Okay, so now I'm going to prove it to you. Okay, I'm going to say these points are trying not to be classified. Okay, I have an algorithm and the points are there. And they're like, dude, don't judge me. Okay? And they're happy if you misjudge them. Okay, they get to go call a lawyer and make a lot of money or whatever. Okay? They're happy when they're misjudged. So a point wins when the algorithm fails on them. Okay? That's like a mistake. Okay? Okay, the learner classifies any weighted majority of the points correctly. So now what I'm doing is I'm introducing weights. I'm going to say this point I care about, this point I don't care about. Okay, those are weights. And now what it says is whatever the weight function it is on these points, any distribution over the points, I can classify them correctly. Half of them, a little bit more than half of them. Okay, that's the assumption. That's a weak learner. It says on any input, I do a little bit better than noise. Okay? Now I'm going to get a strong learner from any weak learners. So first of all, I'm going to just say, well, I don't know any much about these points. I'm going to weight them all equally. Okay? Now I'm going to do this don't worry about the parameters here, but for t rounds. I'm going to keep updating my weights. Okay, they start at 1. I'm going to update them. Okay, so now the algorithm produces a hypothesis that classifies 1/2 plus gamma of the weighted points correctly. Okay? Does that make sense? Does it sound familiar? I said it 3 times. And I always say things lots of times. Okay? But it's good if you ask me again, you can ask me. So what the algorithm does is it produces a program that classifies the points correctly. So you can think of the program as a perceptron, if you want. Right? Okay. Okay, so each point that is correct, you're like, dude, I got this guy. Okay, I don't need to worry about them in the next one. Each point that's incorrect, okay, well, I still care about getting them correct. Okay, so I weight them. I weight the ones that I already know this hypothesis did well on them. I don't need to worry about them. Okay, for the points that I did badly on, I still care. So I'm decreasing the weights of the ones who lost, who I correctly classified. Okay. Okay. Okay, and the answer, my eventual algorithm is I do this for some number of rounds, 1 and 2, and then I just output all these hypotheses and I take the majority. Okay, so I'm trying to do better than 1/2 plus epsilon. Okay. Okay, that's it. That's the algorithm. Okay, again. Like brain dead simple, right? I mean, this is not brain dead simple, but once you get your idea around it, you're like, why didn't I see that? Right? Yeah.
What's mu here? Like, I understand that it's the...
Mu is a parameter. Yeah.
Wait, so how is mu related to gamma?
I don't know. Like, it's going to be related to gamma. Mu is our target.
Like, we can pick it.
Yeah, 0.01.
And gamma
Is no, gamma is a parameter of the weak learner.
Oh, but we're given it by
Yeah.
whatever.
It's just but it could be 0.01 as well.
Okay, and then also, sorry for all the questions, but H2 is the updated version of H1? Like,
H2 is you run the algorithm again on the new weighted func points.
okay, and so on until H2? Okay.
Yeah. Students asking 2 things. What is gamma? Gamma was really more or less epsilon in the previous thing. I should have said epsilon. Okay? But that's fine. Epsilon, just think of epsilon as gamma. Okay? You can vary these things independently, but you don't have to. And then what is H2? H2 is you run the algorithm on the weighted set of points, right? It's a weighted, I don't get all, it's not like I get the same, I'm not running the same algorithm on the same points. I'm saying, well, these points I care less about, and these points I care more about. Okay? And then it gets half weighted on average over that weighting. Okay? And now I take the thing. And now, yeah, so what is, and yes, what is gamma and mu? Think of them both as 1%. So I have algorithms that are right 51% of the time, and I'm going to change them into an algorithm. This algorithm will produce an algorithm that gets it right 99% of the time. Okay? Yeah, no, wait, it's shocking, right? This can't work. Right? Okay, so this is Taylor's expansion. Just to get, I'm going to do some math. So I'm going to show you some inequalities. This is Taylor's expansion for ln. Okay? Because we're multiplying 1 minus epsilon, so that exponentiation happens. Right? So we have to work with exponentials. Okay? So it implies that you have these bounds around logs. ln of 1 minus x, right? We have this 1 minus epsilon that we're going to deal with. Okay, is between minus x and minus x squared. Okay, why is this one here? It's because the first inequality is from a geometric series. It says all of this is not very big. Right? It's smaller than x squared over 2. Right? And that's because you factor out the x squared out of all the rest of this from x cubed on, and this is geometric because x is less than 1/2. It's dominated by geometric. The second is just truncation, right? You're just subtracting numbers here. Okay. X is positive. We're assuming x is positive. Okay, so this is the claim. Okay, these are the bad points. It's where we're failing. Okay, the algorithm is failing. What we'd like is not for there not to be very many bad points, right? That's our goal, is to bring that number, to argue that the number of bad points is small. Okay? Okay, so before I show you the proof is a bunch of math, but the math contains the following intuition. Let's think about one point. Say every other point is good. Okay? And now what would happen to all those other points in the weight function? They would be multiplied by 1 minus epsilon. Okay, so the next time this point is bad again, and now everybody else is multiplied by 1 minus epsilon. This one's bad again. Everyone else is multiplied by 1 minus epsilon, and so on. Eventually, the weighting of everybody else is going to go to 0. And this one's going to be more than half the weight. So for the hypothesis, for the algorithm to work, it has to get this point right. Okay? It's going to pay attention. It's like whack-a-mole, right? The ones that you keep getting wrong, you're like, I'm looking at you, and I'm going to make you be good. Is that clear? The algorithm will focus on the ones that it's failed on previously, and try to classify them correctly. So so these bad points, but it's not that extreme. It's not that there's just one bad. If there's one bad point, you're done, right? We don't even care. It's really it's more subtle because you're only getting a lot of bad points every iteration. Okay, so it becomes more complicated. Okay. 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 So what happens if it's still bad after all of them? You're doing majority, right? That means it's bad. More than half the hypothesis got it wrong on these at any point in the bad set. So more than half the times during the whole algorithm, these points were bad, were misclassified. Okay? Yeah, it's winning. I don't know whether it matters. So it loses less than half the time. Okay? So this tells you that for these bad points, what is their weight? What is the weight for the bad points? Okay, for each one of them, what did their weight start out being? 1. Okay? And it says more than half the times, or at least half the times, it was classified incorrectly and therefore multiplied by 1 for at least half the times it wasn't multiplied by 1 minus epsilon. Right? It just stayed the same. So at most half the times it is multiplied by 1 minus epsilon. Okay? So that's what this says. For each bad point, it's only multiplied by 1 minus epsilon times t over 2. So again, we're using a potential function, right? Before we were using the length of the vector. Here we're using this weight function, the sum of the weights. Okay? Okay, so in this case, for any bad point, its weight is still at least 1 minus epsilon over to the t over 2. Okay. And then you multiply by the number, yeah.
So could you repeat again what WT represents?
WT, sorry, I didn't ever say. WT is the sum of the weights at time t.
Okay.
W of t is the sum of the weights at time t. Okay, each day t, a weak learner penalizes 1/2 plus gamma of the weight. Okay? I mean, it is a nasty calculation, but at least it's short. Okay, so so in general, the weight function is going down, right? Because you're multiplying things by 1 minus epsilon. And in fact, you're multiplying the majority of things by 1 minus epsilon. But you're not multiplying the majority of points. You're multiplying the majority of weight, right? But that's exactly what we're measuring. So we're saying the weight is going down fast because you're multiplying the majority of weight by 1 minus epsilon. Okay? So that's so more than half plus gamma of the distribution of the weight loses. So the weight, the total weight, this half plus gamma of this weight goes down. Okay? So it's the total weight. Most of the weight, I didn't have to do it this way, but this is the way I did it, is some of the weight isn't multiplied by this thing, but some of the weight is. And so it should be 1/2 plus 1/2 minus epsilon. Okay, so that you get a 1 here, and you're saying this essentially is bigger than 1/2 plus gamma. Okay? So it says, and now we use that inequality, that 1 minus epsilon is less than or equal to e to the minus epsilon LT. Okay? So we're using this now. Okay, so all this says, I mean, you have to look at it and stare at it a little bit, but it says more than half the weight is decreased, so you get some decrease in the weight. Okay? This is additive, right? You're just subtracting it off. Now we're going to replace this with an exponential because that's how the analysis works. Okay? We're saying this is bounded by an exponential. Okay, so then we just, this is induction. This says in each iteration you do it. If you go over all iterations, this is why we're multiplying. All right? We're multiplying because, we get this multiplication here, and you get to sum when you multiply, you get to sum the exponents. Okay? And now the sum of the losses over all time, right, these LTs is 1/2 by minus gamma. So you get this expression. I'm just plugging in, and I'm multiplying by capital T because there's capital T iterations. Okay? Again, just to get organized, we're saying the weight is going down fast. Okay, so this is exponentially, it's going down exponentially. Okay? But we know it never gets too small. Okay, the weight is going down, but it doesn't get too small. So that's a contradiction. Eventually, if the weight goes down below what the lower bound is, then there's a contradiction. Okay? Or the lower bound or the number of bad points can't be too big. Okay? So that's what we have. We have the number of bad points here is, the weight is at least this, and it's a function of the bad points. Right? It's at least the number of bad points times something. But it's less than this thing, which is decreasing with time. And now this one is decreasing with time a little faster. Right? Both of them are decreasing with time with respect to t over 2. But this has this extra gamma factor in terms of how it's decreasing with time. Does that make sense? So eventually they're going to cross. Or this number is going to be small. That's the intuition. Okay? So we don't need the weight function anymore. Now we just need to prove an upper bound on S bad. Okay? Okay, so now we just do this. We just work with this, right? We're going to take this epsilon is equal to gamma, and we're going to take logs. Okay, this is a little hard to see. This is first thing we did is divided both sides by n. Because I want to get the fraction. Okay, so then I say, when you take the log of this, you get log of s bad over n times this. And when you take the log of a product, you can take it's the sum of the logs. Okay, so that's what this sum is. Okay, and then when you take the log of the 1 minus epsilon to the t over 2, the t over 2, the exponent comes down. All right, it's just logs. Okay? And same thing here. Here it's easier because you already removed the n over to this side, so you just get the exponent.
You were using like epsilon and gamma are the same, right?
Yeah, right here. Okay? Okay. Epsilon is a way we update, and gamma is the advantage we got from the weak learner. I'm just setting them the same to reduce the number of parameters. They mean different things. Gamma, 1 minus epsilon is our multiplicative factor, and gamma is how good the weak learner is. So, but that's why I'm setting them the same, because I'm optimizing the parameters. Okay. So now we have this inequality from that slide about logs. So I'm just replacing this thing with that. And now you see that this t over 2 minus gamma is the same as this. So we get this. So we get ln of this fraction is less than this thing, right? Less than this thing. Now if you take t, this fraction's, you're worried about the negative? Well, ln of a number less than 1 is negative. Okay, so that's fine. Okay. So now I'm plugging in a t, right? What is this parameter? It's how long I run my algorithm. Okay, that's how many days. So again, you have to worry about convergence. It's always, I don't know did you do convergence proofs, and did you do them in this class? So it's always a little messy, but you can do it, right? And so so then with that it just simplifies, right? I'm canceling the gamma. I get this log gamma. Okay, and that's exactly what I want. I'm saying the fraction of bad points is less than mu. Okay? Because log is an increasing function. Right? Again, the intuition is the points that are bad, they keep their weight. We could have done it the other way around. We could have left everybody's weight and made any weight who was bad, multiplied it by 1 plus epsilon, and done a similar proof. Okay? Okay. Yeah, this is amazing, right? Woohoo! Right? So generic. I didn't assume anything about the algorithms other than they work a little bit. Okay. Sometimes when I'm really excited, I put a lot of explanation points, but I don't know why I didn't do it here. Okay. Oh, okay, we're done. So weak learners learn over distributions. There's some details. The original algorithm has to be able to learn over distribution of points instead of just points. So you can do that by just copying points, right? You can approximate a distribution by just making copies of some points and sort of deleting other points if they're not very interesting in the distribution. Okay? Yeah.
Is that bootstrapping or something different?
What?
Is that bootstrapping or something?
I don't know what bootstrapping is. So I've heard of it. Yeah. So.
I don't know what it is either, sorry.
Okay. Yeah, so you can do this. Often, it's just used everywhere, right? I mean, it's obvious, right? Now you say, wow, like you see this hammer, it is used everywhere, okay? It's a generic algorithm in all these toolkits and stuff like that. Oh, I was going to say there's something missing. Okay, well, okay, so I did have a summary, but But yeah, I just wanted to tell you some algorithms, right? Like in some sense, there's this, oh, you know, you get this mathematician's thing. Oh, that's just, you should solve that with a linear program. It's like, how do you do this? Oh, use a linear program. What's that? Oh, that's like you have to call a program. But no, it's not that hard, right? A linear program, one way you can solve it is you just keep adding the columns in this way. Eventually you'll get there. It's a bad algorithm, won't work fast. But the reason it works is the same as the real algorithms. Okay? So now let's go back. I want to go back a little bit to, right, this simple problem of linear equations, right? We said, in that case, we said, look, AX, right, let's do it again, right? We said, oh, okay, one thing you can do, this is like this residual algorithm, this obvious algorithm, right? If you say, if I have a point x, I set it to x plus alpha b minus ax, right? Does that not now look like this slide in the first convex optimization as I move toward the point? Right? Okay, so now, but what do you really do? Okay, so now the problem with these vectors here is they're all like this, right? Then you like how fast you move toward this point depends on these angles. These angles in high dimensions now get very small. So the convergence rates of these things are bad. Plus, if you have numbers in these matrices, these A's, they can be very small, right? One vector can be very short, one can be very long. You know, it could be very nasty. Okay, so what do you do in practice? Well, what you do is you make all the vectors be the same. You make a basis, right? So, and that's when you do fancier algorithms, and they converge faster. They don't have this sort of slow convergence rates. So all this, the error, these sort of things give you errors on the notion of 1 over epsilon squared. If you want to get the log of 1 over epsilon, then you have to work on the space and make it nicer and multiply by the inverse. Now and the idea is in some sense, if you multiply by the inverse here, you have the solution. Okay? For linear equations, it's multiplying by the inverse matrix gives you the solution. It makes the space so nice, you got the solution already. Okay? But in these other convex bodies, they do things like that. They warp the space using the inverse of the Hessian and move along the thing, right? They just sort of warp this local space so that this works. So all of optimization is essentially some combination of warping the space and Newton's method, where you find the minimum of a quadratic. So what I said now is fairly simple and stuff, but all of it falls into the frame and doesn't fall this part of it. It doesn't cover this frame, but the frame where you use the inverse to modify the local space and you minimize a quadratic, that pretty much covers optimization. Okay, so in some sense, the powerful things you learned intuitively learned in high school or middle school.